Hi, everyone. My name is Nico. I run the visualization team at Uber. I'm going to be talking about geospatial visualization with Viz.gl, and I'll tell you a bit more about what Viz.gl is and a few examples and applications for that. So like Matt said, I run the visualization team at Uber. This is a team of about 35 engineers. Their backgrounds are mostly around information design, computer graphics, WebGL, and web engineering. So, 100% of them do web stuff, but some of them more around the design and UI side, and others more around the computer graphics side. And we develop different data products in collaboration with other organizations for, visualizing self-driving car data, geospatial data, and business data. And as part of that, a part of our team develops open source frameworks, mostly tailored to solving some of the biggest data issues that happen at Uber. But as we've been developing more and more applications at Uber for this, we realize that a lot of these applications can be used externally as well. And so this has, as I'll show you later, has formed really cool partnerships with companies like Mapbox and others. This is the suite of frameworks that we have today. There's more frameworks, but these are the most popular ones. We have Deck.gl, Luma.gl, and React.gl, and then we have a framework that we've been developing to visualize perception, prediction, and motion planning data for self-driving cars. That's called avs.auto. I'm not a big fan of that name because it's called Autonomous Visualization System. It's very obvious as a name, but we couldn't pick another one. Cool, so I'll quickly walk you through these 4 sections. Kepler.gl, which is an application and the framework to visualize geospatial data. Then how to build applications with React.gl and Deck.gl. This allows for more customization. I'll show you next how to do that. Then we'll dive into more lower level WebGL stuff with Luma.gl, and I'll show you an example of how we can use that to do even more custom things. And then finally, I'll give you a quick peek of a framework that's going to be released end of this month. That's called avs.auto. It's a framework and a standard. It's actually pretty cool. So Kepler.gl, all of this is open source. If you go to Kepler.gl today, you'll be able to access it. To give you a quick idea of what you get to see, if you go there, you see this application right here. You can hit it, get started. You can try to drag and drop your CSV file, or you can try a few examples just to give you an idea. Since we've had an earthquake this morning and last morning, I'll just show you an earthquake example. These are plenty of earthquakes. Some of them worse than what we had this morning, I'm sure. And you on the left, it's like Photoshop for maps in a way. On the left, you have multiple layers that you can use. That's a data set. You can map those layers to different visual marks and channels. So you can say I'll map every latitude and longitude to an XY coordinate into a scatter plot layer. This is exactly what's happening with this earthquakes kind of visualization. And then you can apply filters. So for example, here we're looking at earthquakes for a given time range. You can change that through time. You can change the different windows for those times, or you can play it. And so it all animates pretty smoothly. And so the offering that Kepler.gl has today is the fact that it gives you a lot of power to visualize and explore data through the use of the GPU in the browser through WebGL. And it does this through using this WebGL feature that's called instancing. Cool, that's one example. There's plenty more examples, but I'll tell you a little bit what people have built with it, just to give you an idea of what you can do with it as well. This is an example of somebody looking at building footprints and 3D structures on Kepler.gl. These are folks visualizing energy consumption, people visualizing pickup and drop-off, heat map data, folks visualizing cell phone network data, folks visualizing real estate information, and the list goes on, trees, KML files, and other types of information. So the list is actually pretty big, and the spectrum, it varies quite a bit, but most of the folks using these are people who are into GIS or folks that are trying to visualize some sort of data set on top of a map. Back to the presentation. So as I mentioned before, we launched this with partnership with Mapbox at their main event located earlier last year. And it got a really good reception. You've seen some of the use cases that organically people have been, applying this for. Internally, you can also use Kepler as a library, as a framework itself. It's like a Redux connected component, so it comes both with as a React component, and it comes with its own like store as well that you can hook into your own store. People have used this at Uber to build their own custom web applications, but also like to embed, for example, Kepler into Jupyter notebooks or other types of notebooks as well. The idea here is that you add Kepler. Kepler.gl has a family of components. One of them is the map, but you can import other components. You can put them within your other components in your app, and then you can hook your reducer to the Kepler.gl reducer. These are some of the things that are being offered by Kepler. So you have, map container, side panel, bottom widget, modals. All of these things are swappable or removable. You have a bunch of reducers that capture state for your visualization, your map, the UI, and the map styling. And then you have a bunch of interesting and useful utility libraries for exporting a map into an image, for example, or file handlers to parsing different file formats, and etc. So it's fairly modular in that sense. One cool thing is that you can have multiple maps in the same web application. We've had that with like side-by-side maps that interact and are synchronized with each other. So then you can have multiple reducers as part of the Kepler.gl reducer. So it's like sub-reducers. This is how it looks like. Number one, you mount your Kepler.gl reducer in your own app reducer through this combined reducers piece. And then secondly, you just use your Kepler.gl component within your app. And then you can just dispatch custom actions to your Kepler.gl reducer. Cool. So that's the first section, and it covers how to use Kepler.gl both as an application that you can just go there and use it and dump like a CSV file, or how to use that within a larger web app. If you were to get or wanted to have more customization, you wanted to build your own layers, you want to visualize data in a more unique way, then you would probably try to use a combination of two libraries. One is React Map.gl, which is a really friendly wrapper around Mapbox.gl.js, the library using WebGL from Mapbox. It provides a React-friendly interface for it. And then you would use probably Deck.gl if you wanted to have the kind of the power of the GPU to render like hundreds of thousands, if not millions, of data points. So this would be the combination I would go with. All these companies use Deck.gl in some form or another, whether they want to admit it or not. And so some of them are very public about it. Some are not, but they tell me through coffee meetings. And so it's actually pretty cool to see that some of these libraries can get traction externally, and can visualize data from other companies as well. Like why not? Two examples that are pretty cool using Deck.gl. One is by this Movil Labs team in Germany. They've been visualizing flights paths through Deck.gl. So this is a full like 3D immersive like type visualization that you can use for that. And then other startups, this one based out of New York City called Foam.space. They use kind of blockchain to give you proof of location. So it's like you cannot GPS spoof where you are because it's using blockchain in some way. And they do the entire explanatory visualization through Deck.gl. Sorry, that's as much as I understand. So Deck.gl comes with a big set of built-in layers. You have common visual marks and channels to encode data, right? You have circles or points, you have different types of heat maps, bucketed by squares, bucketed by hexagons, etc. So these things are already covered in Deck.gl, and you can just import this layer. In this case, we're importing, for example, the scatterplot layer, and we're visualizing a bunch of like, I think in this case, it's like a CSV file. And it's very much D3 style, where you can get all the accessors and you can shape the radius of the circles based on different data sets. Lately, what we did is to get full independence from React. And actually that opened the door to like a new crowd of people that were coming from the WebGL world and not necessarily were leveraging a lot of the React stuff. Also made it easy to just use with Observable or CodePen or other places where you just want to drop in Deck.gl and create a quick prototype. So you can both use it with React or with pure.js. This is an example I built a while ago, visualizing wind. So this is an example of why it would be useful or why it would be interesting to explore like custom layers. So in this case, we're visualizing wind and wind elevation and wind as different waves, like as a vector field and as a set of particles. But what's interesting about this is that the data set is not uniformly distributed across the US. You have every yellow dot there is a wind station, and it captures temperature and direction and wind speed per hour. And what we did here is we actually used a layer from Deck.gl to process this data and generate a vector field where you could just query anywhere in the map. Given a point in a map, I could give you the exact information around interpolated data around wind speed and direction and temperature. So from that we created this vector field, and then as you change the time, the vector field is all interpolated, and then as you add, you can use that very same vector field with a different visual metaphor, which is particles, and you can start throwing like one of these, like I think there's 1 million particles there, and see how kind of the wind pushes those particles with some sort of physics. I'm gonna change my tab because if you leave it open with WebGL, it crashes your browser, just so you know. So as I mentioned before, one of the challenges that we had was that we had all these wind stations, right? These like blue, green, and red dots. And we wanted to see what were the interpreted values for wind speed, direction, and temperature in all these like sort of like question marks. And we could use the power of the GPU to do that. We could assign a color channel, let's say red, green, or blue, to each value of wind speed, direction, or temperature. And then we could render that into an image. And what's really cool is that the rendering pipeline has this sort of like automated process that happens in the GPU, which is the kind of triangle assembly process and rasterization process, where it actually interpolates, like in this triangle that you see on the right, every one of those colors throughout that triangle. So finally you get an image of where every pixel gives you an interpolated value of that data set. So this is an example of the image that we've generated without the filling pattern. And again, we've partnered with Mapbox. So they just released a new API that's called Custom Layers, where we work with them actually to encourage them to expose their WebGL context so that you could write custom layers within Mapbox. So if you know WebGL, kind of raw WebGL, you can write WebGL to create your own custom layers within Mapbox, or you can leverage Deck.gl as custom layers themselves and use that API to create new layers that you can use with Mapbox. Cool. So the third case is library is called Luma.gl. So Kepler.gl and Deck.gl leverage Luma.gl. Luma.gl is a more abstract framework in a way. It is lower level. The main idea behind Luma.gl is that you have a set of utilities and functions and classes that mimic or map to the WebGL2 API and specification. So if you are to develop with Luma.gl, you kind of like need to have as a requirement some sort of WebGL experience. But that doesn't, you shouldn't be stopped by the fact that if you're not very familiar with low-level WebGL, you should not do this, because it's also a good entry point to learn WebGL, since it has a lot of like interesting lessons and examples that are fairly simple, written up in Luma.gl code. As you learn more about the Luma.gl API, it's an easier process to get into the lower level kind of a WebGL API. So one example of how we I used Luma.gl to try out new things that were outside of the scope of things that you could build, for example, with Deck.gl, was this problem of map projections, right? So why are there so many map projections? There are map projections because you have a trade-off between different things about how to map the 3D world into a 2D plane, right? So basically you have two types of projections, ones that distort area and ones that distort angle. The ones that distort area and do not distort angle, they're called conformal mappings, and the other ones, I don't know, I think they don't have a name. Anyways, the ones that distort area, you can see them here, like the classical Mercator projection, how much they can lie, right? As you approximate this huge piece of land to the equator, you see actually how small it is. And you get to see the actual distortion in area on the left. These are called Tissot indicatrix, and they tell you how much the area is affected as you move up and down this circle. So to recap what I mentioned before, on the left side of this triangle, you have equal area projections. Like on the leftmost side, you have like this equirectangular projection where you see that the area will remain the same, but angles will get distorted. And then on the right side, you have Mercator projection, which is conformal projection. It preserves angles, but the area is distorted. And then this kind of like PhD person asked himself like whether he could have both equal area and conformal projections. So whether there was a point at the top of that triangle that you could reach, and he created this thing called myriahedral projections. So these are a few examples of myriahedral projections, but I'll show you a demo of that. So as you can see, myriahedral projections like preserve angle and area, but the bad thing about them is that you get a lot of interrupts. So these are plenty of cuts within the land that you get from these. But you can mimic a lot of like existing map projections. Like this is similar to a polyconic projection. This is similar to a normal projection that you would get in a map. And this is like a azimuthal projection, so looking from the South Pole. Or you could have projections where you want to preserve the land mass into one piece, and you cut over the oceans, for example. So the initial mesh that you use for those projections will kind of influence how the projections will look like. These were created with the graphical mesh, right? Where the edges for that mesh match the parallels and meridians of the globe. But you could also like start with platonic solids, right? Like say you have a tetrahedron or an icosahedron. Please don't let me say these words more. And then you subdivide them multiple times, right? You get to have different shapes for these things. So for example, in this case, if you got a tetrahedron and you kind of subdivided it multiple times, you'll get something like this, where you have 4 faces, right, mainly, and then they get subdivided 4 times more and so on. And a cool thing is that you can visualize also different things. So you can look at the dual graph and the cuts and folds. So the dual graph is used to preserve connection between the faces, which is the blue thing, and the red thing is where the cuts actually happen. And then finally, something that's kind of interesting too is that you can also change the origin of that projection. So you hit shift and move your mouse, you can change kind of like where that projection is originated. And you can do that with multiple other projections too. Cool, so I talked already about the meshes. Here, red lines are cuts, blue lines are folds. Another thing that we used in this paper to implement it was to try to get optimal mappings, which is ways to cut these platonic solids in a way where they would not cut the landmass. So we found ways to map the Earth in a way that it would be preserved in one piece. And then I did some digital fabrication stuff. Finally, I wanted to, so we're going to be releasing this framework soon. It's a really awesome framework. I'm very excited about it. It's both a data standard for streaming and processing data around perception, prediction, and motion planning information for self-driving cars. And then the other piece is also like a client-side JavaScript drop-in library that you can use if you encode the data in that format, which I feel it's pretty powerful. And we used it at Uber. The Advanced Technology Group is using it in a variety of different projects. And then we've also partnered with other companies externally who are already implementing the data in this format and are using our tools for this. So demo of that is this. So there's this data set that's called the Kitty data set. Kitty data set contains perception data above all of a vehicle. And let's see if you can, this works kind of like a video in a way, but this is all data streaming. And so you get to see the LiDAR point cloud data. The boxes and their colors are the objects that are being detected and tracked by the vehicle. The green band there is kind of like the motion planning for that vehicle, like whether to follow the vehicle that's in front of it or to do some other heuristic as it's driving. And then the yellow lines show the prediction data, right? Like where the car thinks that all these different objects are going to be in the future. And at any time you can kind of, this is fully interactive, you can change your camera modes. You can see it in first person. You can choose a change it here. Oh, sorry, it's locked. And then you can also visualize, you can click on the objects to get information about them. And then you get to see here on the left, different charts for like velocity and acceleration for the data for each one of the objects in the vehicle, and the different data streams that come through that format. Let me actually do this. I don't think I have enough time to explain this, but in summary is you have a car that gives you data in almost real time, and then you have some sort of store that could store other stuff, like let's say a map, right? That doesn't change in real time, and then you combine these two, and then you serve them into this thing we call XViz, which is a protocol and a standard for encoding that data, and then you use a client, which is on the right, to just like visualize all this information. Cool, thank you. I'm gonna be around for answering questions later tonight.